little sketches of the equation by tonight on Piazza. All right, so we were looking at the interval scheduling problem. If you remember here, the problem is you're given n intervals. The ith interval has a start time of Si and a finish time of Fi, with the convention that you need to finish strictly before the finish time. And you want to output a schedule of these n intervals. A schedule is nothing but a subset of these n intervals. And it's a valid schedule if no two intervals conflict. So if you kind of draw them out, they don't overlap. And you want to output a valid schedule that maximizes the number of such intervals in the schedule. Okay. So we looked at the following greedy algorithm last time. So let's say R is my initial set of requests, and I have this set S that I'm going to build. That's going to be my final schedule. So I initialize it to be empty. And while there are still intervals that I have not handled, you choose the interval with the earliest finish time, you add it to S, and then you remove all requests that conflict with I from R. Remember or note that by definition, a job always conflicts with itself. So when I say remove all that conflicts with I, at the very least you will remove I from the list. And finally, the final output is, I'm going to call it S star. So we argued last time that S star has no conflicts, and we're starting to argue that S star is indeed an optimal solution. So the way we're going to argue this is by this proof method that I'll call greedy stays ahead. While I take this stuff from Eshani, why don't you guys look at it, let me know if you have any questions. All right, any questions on the algorithm? Is everyone okay with the greedy algorithm? All right, so today we are going to use this greedy stays ahead technique to argue that the output of the greedy algorithm is optimal, i.e. It is a valid schedule that has the maximum number of possible such schedules. And then we're going to start trying to analyze the runtime of this video. Okay. All right, any questions before we start? Okay, so again, reminder of notation. S star is the output of the greedy algorithm, and scripto is an optimal solution. Again, remember, as mentioned last time, you could have more than one such possible optimal solutions. So you cannot hope to prove that the output S star is exactly equal to this optimal solution O that someone has given you. So what we can prove though is that the size of these two sets are the same. So we'll prove correctness if we argue that the number of intervals scheduled by the greedy algorithm is exactly equal to the number of jobs scheduled by the optimal solution. Okay. So to do this, just to avoid writing size of sets all the time, I'm going to assume that S star is the jobs indexed by I1 up to IK, and optimal is J1 up to JK. Again, remember, we are sorting everything by the finish time. So these I1 to IK are also ordered by finish time. Similarly, J1 is less than or equal to F of J2, so on and so forth. Oh, sorry. M. So we are assuming that S star has K guys, and the optimal has M guys. So just to ensure everyone's on the same page, how do you express theorem 2 in terms of K and M? Evan? Yeah, so you have to argue that K and M are exactly equal, right? Again, remember, these are the sizes of these two guys. Okay, so in terms of this notation, we want to argue that K is equal to M. Right? So this is an equivalent formulation, but we're going to go with that. All right. So I claim that by definition of optimal solution, K is less than or equal to M. Is everyone okay with that claim? Yes, no, don't care. Good? All right, again, just as a reminder, by definition, O is an optimal solution. We do not know yet, or we have not proved yet, that S star, the output of greedy, is also optimal. Right? So all we can say at this point of time is that the number of intervals in greedy cannot be more than the optimal by definition. Okay. So as by definition, O has the maximum number of intervals in any valid schedule. And again, of course, we're using the fact here that the output of the greedy solution is also a valid schedule. Okay, everyone okay so far? Oh, Angus. M is the number of elements in O. So the sets in O is J1 up to Jm. Any other questions? Yeah, so this quantity is supposed to be J of M. So to prove this theorem, we're going to need another lemma, which is going to be the formalization of the greedy stays ahead for this specific case. And the lemma says, you look at any of these guys in S star, and if you look at the finish time of the nth guy in S star, that's always going to be before the finish time of the nth guy in this optimal solution. Okay. So the greedy says that says, you can line them up. So we know K is less than or equal to M. So if you line them up, at least the first K guys, you can have one-to-one correspondence between S star and O. And what that's saying, what the greedy stays ahead lemma says, is that if you look at any of the first L guys, the Lth guy in the greedy solution will finish before the Lth guy in the optimal solution. Okay, so in that sense, greedy always stays ahead. It's always finishing before the optimal solution. So the way I'm going to go with this is we're going to assume that this lemma is true. Assuming this, we're going to prove the theorem, and then we're going to come back and prove this lemma. Okay? All right. So again, we are going to prove the result that k is equal to m, and we are going to assume lemma 1 is true. And again, no surprises here. We're going to prove this by contradiction. Okay? So we're going to prove by contradiction. So we know by the claim that k cannot be strictly more than m, it's less than equal to m. So if we know k is less than equal to m and if we assume for the sake of contradiction that k is not equal to m, then by the claim that implies k has to be strictly smaller than m. Okay? So assume k is not equal to m, then by claim k is strictly less than equal to m, or equivalently m is greater than equal to k plus 1. Okay. So this is another long-winded way of saying, let's assume that the optimal has at least one more job in it than the greedy solution. Okay. And so assuming this, we want to come up with a contradiction where we're going to use lemma 1 for our argument. So since there is at least one more guy, this implies that there is a k plus 1th guy in the optimal solution. And now let's look at how things look at the end, or at the kth and k plus 1th guy. So I'm going to draw S star on top here and the optimal over here. So we know S star ends at the kth guy, so I let ik be the last guy. I also know that by the greedy stays ahead argument, the kth guy in greedy will finish before the kth guy in the optimal. Right? So if I draw j of k, I don't know much about the start time of j of k, but I do know for sure that it cannot finish strictly before the I of k. Okay, so the finish time will come after this. And not only that, we know that j of k plus 1 is in the optimal solution. So here's the situation. So there could be even more guys in the optimal solution, but we don't care about that for now. We know that S star finishes at ik, which by the greedy stays ahead lemma will finish before the kth guy in the optimal solution. And there's going to be another guy in the optimal solution, the k plus 1th guy, that is going to be disjoint from the kth guy in the optimal solution. So this we know by lemma 1 and by assuming that k is not equal to m. Okay. I said, so by lemma 1, finish time of the kth guy is before the finish time of the jth guy. And so now what we want to think about is, consider the case when the algorithm is done adding the kth guy. This is the greedy algorithm. Okay. So consider the time when greedy adds ik to S. And so if we look at this situation, j of k plus 1 does not conflict with I of k. Okay? And indeed, it will not conflict with anything that comes before I of k either. In other words, j of k plus 1 is one interval that doesn't conflict with any of the first k guys in the greedy algorithm, which means it still has to remain in my set R, where the greedy algorithm key tracks are the guys that have not been dealt with. Okay? So the point is here, j of k plus 1 is in R, And so that implies my set R is non-empty. So that implies greedy cannot terminate after adding I of k. Okay, so this is a contradiction. And again, remember, we are assuming that S star has the quantities the jobs I1 to Ik, and the fact that you have your hands on S star automatically means that the algorithm stopped at that point of time. Okay. And so that's the argument. So that's the proof of the correctness, assuming that lemma 1 is true. So talk to your friends for half a minute. Let me know if you have any questions. If not, we'll move on to proof of lemma 1. Are there any questions? So everyone convinced that the greedy algorithm outputs an optimal solution, assuming lemma 1 is true?
Don't you need a second? Don't you need a second claim saying that it's not, like k is not greater than m?
So my question is, don't you need a claim that k is not greater than m? No. So the claim that k is less than or equal to m automatically follows from the fact that m is the size of the largest possible valid solution. Right, so k can never be bigger than or equal to m because greedy also outputs a valid solution. So by definition of optimal solution, or by definition of m, any valid solution cannot have more than m. So it's always less than or equal to m. What we are proving here is it cannot be strictly less than m. But if you are, okay, let me go back. Are you trying to say that you could have proved k equal to m by proving k bigger than or equal to m and k less than or equal to m?
No, I was just asking because we're trying to prove it's equal to m. So
right.
If we prove it's less than or equal to, that's kind of proving.
No, we did not prove it's less than or equal to. So we assume for the sake of contradiction that k is not equal to m. Then that always immediately implies by the fact that k cannot be strictly more than m, that k is less than or equal to, strictly less than or equal to m. So what I'm saying is we argued that k cannot be strictly less than m. And by definition of m, it cannot be strictly more than m.
I think I get it.
This is if there's a confusion about this, I'd like to clear this because this kind of argument will happen like 10 times in this course. So better to get it out of the way now rather than be confused now and still remain confused later on. Any questions on this proof? Okay. So now we want to prove lemma 1, which says you look at the Lth guy in, again remember these are sorted by the finish time. You look at the Lth guy in the greedy and the Lth guy in the optimal, then the finish time of the Lth guy in the greedy is always less than equal to the finish time of the Lth guy in the optimal. So we're going to prove this again as a proof idea for lemma 1, and we finally break the shackles of contradiction by using induction. So we prove by induction, and we'll prove it on the value of L, the size, this index L, which goes from 1 to k. So the base case, we want to argue that f of I1 is less than equal to f of J1. I claim this is true, and my question to you is why? Oh, Evan, sorry.
Because by definition of the algorithm, we would have picked on the first iteration the thing that finishes the first.
Right, so as Evan said, if you look at the definition of the greedy algorithm, by definition, it's going to pick the very first choice is going to be the job which has the earliest finish time. Okay. So this is true. So by definition of algorithm, I1 is the job with the earliest finish time. I actually even note that I1 actually will be equal to 1, because remember we had sorted all the jobs by the finish time, and we were picking at the very first step you will pick the job with the smallest index, which just happens to be 1, which again by the fact that they are sorted by the finish time will be the job with the earliest finish time. Okay. So just by the definition of the greedy algorithm, the finish time of the first guy in greedy is before the finish time of the first guy of the optimal solution, and indeed it's true for any other job too. So now we want to prove this by induction. So for the inductive hypothesis, assume that fi of L is less than equal to fj of L for all L from 1 to R. So we're assuming this is true for values of L up to R, and next we want to argue that this is true for R plus 1. So the inductive step want to show the finish time of the R plus 1th guy for the greedy is no more than the finish time of the R plus 1th guy for optimal. Okay, so this is what we want to do. Any questions so far? All right, so it turns out that even though I said we'll break the shackles of proof of contradiction, it's not going to be a clean break because we're going to argue the inductive step by contradiction. Okay, so for the sake of contradiction, assume that this doesn't hold true. So assume the finish time of the Rth guy in greedy is strictly more than the finish time of, R plus 1th guy is strictly more than the finish time of R plus 1th guy in the optimal. And what we're going to do is again draw a picture to kind of figure out what the various situations are and then come up with a contradiction. All right. So we have S star and we have optimal. By the inductive hypothesis, the Rth guy in greedy finishes before the Rth guy in optimal. And now we are saying, but if you look at r plus 1th guy, it finishes strictly after, the r plus 1th guy in greedy finishes strictly after the r plus 1th guy in optimal. Okay, so again, the fact that this finishes before this just follows from the inductive hypothesis. And the fact that this guy finishes after this just follows by our assumption for the sake of contradiction. Okay. And so now what we're going to do is kind of a similar thought process as we did when we did the proof of the theorem, which is we're going to say, well, let's see what greedy algorithm, what is the situation for the greedy algorithm after it has added the rth guy. Okay, so consider the situation after IR is added to S. Again, you note that this J of R plus 1 is something that has also not been scheduled yet, right? Because this doesn't conflict with J of R, and since J of R finishes after I of R, it means J of R plus 1 cannot conflict with I of R, and indeed cannot conflict with anything that comes before. So we have indeed that both I of R plus 1 and J of R plus 1 is in this capital set R after little IR has been added to the set S. So this is the situation. Greedy algorithm has added IR to set S, but it still has these two jobs, J of R plus 1 and I of R plus 1 in R. Now, at the next step, what the greedy algorithm will do is pick the jobs among R that has the smallest finish time. And the fact that it picked I of R plus 1 instead of J of R plus 1 has to mean that it has an earlier finish time. Okay? And so, since greedy chose I of R plus 1 over J of R plus 1, this has to imply that the finish time of I of R plus 1 is less than or equal to the finish time of JR plus 1, which is a contradiction. And we are done. So this proves the greedy stays ahead lemma, which in turn proves that the number of intervals that are in the greedy schedule is the maximum possible. In other words, it's an optimal solution. Okay, so I'll let you talk to your friends. Talk to your friends for half a minute. Let me know if you have any questions. If not, we'll move on to analyzing the runtime of this algorithm. But at this point, we are done with arguing with the proof of correctness for the greedy algorithm. All right, are there any questions? Everyone okay with proof of correctness for the greedy algorithm for the interval scheduling problem? All right, so let's do runtime analysis. So it turned out that it's fairly easy to show that you can solve this in order n squared. And there's one cute observation that you make, that you can then bring the runtime down to n log n. Okay. So again, just as a quick reminder, here's the greedy algorithm. You initialize the set R to everything. You initialize your final the set of schedules to be empty set. And while you still have items or intervals that you have not dealt with, pick I in R with the smallest index. And again, reminder that we have sorted everything so that when I pick the interval with the smallest index, by definition, it will get you the guy with the smallest finish time. Add I to S and remove all j in R that conflict with I. And at the end, you return this set S that you currently have. Okay. So now let's just, so here you're just initializing a set with n elements. So this is order n time. You're just emptying a set to be the empty set. This is constant time. At the end, you're outputting a set. Now note that this set could be pretty large. It, for example, could be all the intervals. So in the worst case, even just outputting this set will take order n time. Then notice that in this, in any one iteration, you're deleting at least I, right? So the guy that you're picking here will get deleted in this set because I conflicts with itself. Okay? So in each iteration of the loop, you are throwing away at least one vertex, which means you cannot run this loop more than n times. Okay? So this runs less than equal to n times because step 2.3 removes at least one interval. Okay. And so then the question is, I have this set R, and notice here that you have no guarantee on what this set R could be, right? So it's not that they're going to be contiguous indices, say from 10 to 100. I mean, you could have like 55 not being there just because it had conflict with something. So in general, this set R could be of a fairly big size, right? So it could be again of size n. And so if you want to find the minimum, say index among all the n up to possible n values, you can again spend up to O of n time. So picking this smallest index in the worst case can take O of n time. Depending on your data structure, you can actually even assume that adding a new element to the set only takes constant time, but no worse than order n for sure. And then you have to go and check all the intervals in set R. Again, in the worst case, there could be up to n of them. Check whether they conflict with I. Checking for conflict is constant time. And then if it conflicts, then remove. Right? So in the worst case, you're going to deal with n elements in R, and you're going to do some constant operations on those. So this is again order of n. So overall, you have order n plus order 1 plus n times order n plus order n. Okay. So in the worst case, you end up with O of n squared. Yeah, Evan.
Isn't R sorted?
Evan's question is, isn't R sorted? R, you could potentially keep it sorted, but we have not specified what the data structure for R is yet either, right? So you could potentially do it, right? But even then, step 2.3 would still take order n time in the worst case if you're not careful, right? Because you have to walk through all of it. So it turns out the place that we are losing a lot of time in this kind of way of thinking about thing is step 2.3. Okay? And we're basically going to argue that yes, there could be one iteration where you have to throw away omega n guys, but we're going to show that overall, if you're smart in kind of throwing away stuff, the moment that you only have to throw something away at that point of time, then overall iterations you can do it in O of n time. So next time we're going to unpack this and show that you can do it in O of n log n over.